This might get a little technical, but it's just another fascinating aspect of what's going on and how there is so many angles to this artificial intelligence explosion happening. We are just scratching the surface as to the many tangents this research will take to help improve things. Hope you enjoy a little tech talk.
Absolutely. It feels like every week there's some new angle, some clever optimization.
Totally. And today, yeah, we're diving into something called sleep time compute. It's based on this really interesting paper, Sleep Time Compute, Beyond Inference Scaling at Test Time by Lin and colleagues.
Right, I saw that one. It's a pretty neat concept, basically trying to make AI models more efficient by, well, letting them think ahead.
Think ahead. Yeah, that's a good way to put it. It's about enabling these models to sort of pre-process information before you even ask them a question during their downtime.
Which is quite different from how things mostly work now, isn't it? The standard approach is all about test time compute.
Exactly. Test time compute, that's when, you ask your question and then the model, like the ones from '01 or '03, DeepSeek, even the new Gemini 2.5,
Yeah.
starts churning.
Great. It spends time, sometimes a lot of time, generating those thinking tokens, as they call them, reasoning things out while you wait.
And that's the catch, isn't it? It can be slow. We're talking seconds, maybe even minutes for complex stuff.
And expensive, because those GPUs are running full tilt during that whole query process. More processing time equals higher costs, higher energy use.
Okay, so why is that the dominant way right now? Why all this calculation on the spot?
Well, the paper points out a key assumption that problems are often treated as stateless. Like the model forgets everything the moment it answers.
Stateless, meaning it starts completely fresh with every single query.
Pretty much, even if you feed it the exact same chunk of text, the same context, 5 times in a row.
Huh. Like imagine querying a code base, right? You ask about function A, then function B in the same file.
Yeah, even if you have some caching, the model might still redo a bunch of the basic understanding of that code each time.
Yeah.
Well, it can be redundant.
Okay, but the paper argues this isn't always how we use LLMs. They talk about stateful applications.
Exactly. Stateful. Think about document Q&A. You load a PDF and ask 10 questions about it.
Or a coding assistant. It needs to remember the whole project context over time.
Or even just a chatbot that remembers the last thing you said. The context persists, it's reused.
So if the context is already there, sitting around.
Why not use the model's idle time, its sleep time, to work on that context? That's the core idea. Pre-process it offline.
Okay, I need an example. The paper had one, right? The juggler.
Yeah, the juggler example. It's pretty good. And there's a YouTube video, too, that helps. So the raw info is like, a juggler has 800 balls, a quarter are tennis balls, half of the tennis balls are indigo, and a tenth of those are marked.
Right. So normally if I ask how many marked indigo tennis balls,
The model crunches that whole statement. Then if you ask, okay, how many tennis balls total, it crunches the whole thing again. That's test time compute.
but with sleep time compute.
The model looks at a quarter are tennis balls for the 800 total. And during its sleep time, it calculates, okay, that's 200 tennis balls.
Oh, okay. And it keeps going.
Yeah. It sees half of the tennis balls are indigo, so it figures out, right, 100 indigo tennis balls. It pre-calculates these useful facts from the context.
Got it. So then when I ask how many mark indigo ones,
It already knows there are 100 indigo tennis balls. It just needs to apply the 1/10 are marked part. Boom, 10. Much faster at query time.
and if I ask how many tennis balls, it just pulls out the 200 it already calculated.
Exactly. The heavy lifting, or some of it, is done beforehand when the GPUs might have been idle anyway.
And that saves money because idle time compute is cheaper.
Potentially much cheaper. That video you mentioned suggested latency optimized inference. The real-time stuff can be roughly like 10 times more expensive. So shifting work to sleep time could be a big cost saving.
Wow, 10 times. Okay, that's a serious difference. So this sounds great in theory, but did they actually test it? What's the evidence?
Oh yeah, they ran experiments. They took some existing math problem data sets, GSM, symbolic, and AIM, and kind of reformatted them.
Reformatted how?
They split the problems. So the initial setup, the given numbers and conditions, that became the context, and the actual questions you need to answer became separate queries. Made it stateful, you see.
Right, to mimic having context first, then asking questions. Figure 2 in the paper shows an example, I think.
And they also made a multi-query version of one data set. That was to see what happens when you ask several related questions about the same context, which is super common.
Makes sense. And which models did they try this on?
A whole bunch. different GPT-4 versions like O-Mini and the regular O, O1, O3 Mini, Claude Sonnet 3.7 with extended thinking, DeepSeek R1. Quite a range.
Okay, the results. What was the big finding?
The headline is pretty striking. Sleep time compute could cut down the amount of test time compute needed to get the same accuracy by about 5 times.
5 times, just
Wow.
by pre-processing.
Roughly 5x, yeah, on both their stateful math datasets. That's a big potential reduction in that expensive real-time processing.
Okay, wow. Anything else?
Yeah, interestingly, they found that if you invest more compute during sleep time, do more pre-processing, you can actually boost the final accuracy.
So more thinking ahead equals better answers later.
Seems like it. Up to maybe 13% better accuracy on one dataset and 18% on the other in their tests. Figures 3, 4, and 7 show these scaling effects.
It's like studying harder before the test pays off.
Kind of, yeah. And remember that multi-query setup?
Right, asking several questions about the same context.
They found that by doing the sleep time work once, you could lower the average cost per query by about 2.5 times across multiple questions because you amortize that initial pre-processing cost.
That makes total sense. You pay the upfront thinking costs once, then reap the benefits for several related queries. Figure 9 shows that, you said.
Illustrates the cost saving per query as you ask more.
Did they figure out when this works best? Like, are there situations where it's more or less useful?
Definitely. They found it's most effective when the user's question is kind of predictable from the context you give the model.
Predictable. How so?
Like, if the context strongly hints at the types of questions that are likely to follow, if the AI can make a good guess about what you might ask next, pre-processing for those likely questions is really efficient. Figure 10 and Appendix E have some examples comparing predictable versus unpredictable scenarios.
So if I give it a recipe, it might predict I'll ask about ingredients or baking time and pre-process related info.
Exactly. But if you give it the recipe and then ask about, I don't know, astrophysics, the pre-processing about flour ratios won't help much.
Right, so predictability matters. Did they compare this sleep time idea to other ways of improving performance?
They did. They looked at something called parallel test time scaling, or PASEC-K.
PASEC-K, isn't that where the model generates like multiple possible answers at test time and tries to pick the best one?
Precisely. It generates several candidates in parallel, but the study found that sleep time compute actually performed better than PASEC-K when they were given the same budget of test time tokens.
Better. So pre-thinking beats generating multiple options on the spot, at least for the same cost.
In these stateful scenarios, yes, that's what their results suggested. Figures 5 and 6 show that comparison.
Okay, so it works well on these math problems. Did they try it on something more real world?
Yeah, they did a case study using a software engineering task. They used a new benchmark called SWE features.
SWE features. What's special about that?
It focuses on tasks like adding a new feature to software that requires changes across multiple files, which is apparently more realistic than some older benchmarks that just look at single file bug fixes.
Okay, so how does sleep time compute fit in there?
They used past pull requests, proposed code changes from relevant projects as the context.
Ah, so the history of related changes. And the query.
The query was the new pull request, the new feature that the AI agent needed to implement or understand. They even looked at repos like Aider AIs and Comfy UIs where PRs are often clustered around related features.
Clever. Using related past work as context. And did the sleep time pre-processing help?
It did, especially when they limited the amount of compute allowed during the actual test time.
So with a tight budget for thinking on the spot.
Yeah. Sleep time compute improved the model's ability to predict which files would need changing for the new feature. They estimated it led to about a 1.5x decrease in the test time tokens needed for similar performance. Figure 11 shows this.
Interesting. So even a 1.5x improvement in a complex, real-world-ish task is pretty notable.
Definitely suggests the principle holds up beyond just math problems.
So let's sort of zoom out. What are the big implications here? What's the main takeaway for, people listening?
Well, the core benefit seems clear, potentially making these big AI models cheaper to run and faster to respond, especially for applications where you have ongoing context.
Like the document Q&A, coding assistance, long conversations.
Exactly. Anywhere the context sticks around and you ask related questions, that's where the biggest wins seem to be.
But there's a catch, right? We talked about predictability.
Right. The trade-off is that it's less useful if the questions are totally random and unrelated to the context you pre-processed. If the model can't anticipate, it can't prepare effectively.
Makes sense. So what's next for this idea? Where does the research go from here?
The paper suggests a few things. One big one is figuring out how to automatically tell which contexts are likely to lead to predictable questions.
So the system could decide when to invest in sleep time compute.
Yeah, and how much compute to allocate. Finding that optimal balance between pre-processing and on-the-spot thinking.
Are there other potential directions?
They touch on maybe extending it beyond just context query splits, handling more complex stuff, and they even frame it as a type of representation learning. Like the model is learning more deeply about the data during its sleep time.
Learning better representations that could have broader benefit.
Could do. And maybe even using it for things like generating synthetic data more efficiently. Lots of possibilities.
It really does feel like another clever way to squeeze more efficiency out of these systems. It challenges that idea that everything has to happen right now.
Proactive versus purely reactive computation. It's a smart shift in thinking.
So the key takeaway for you, listening, is that this sleep time compute idea is a really promising approach. It's about letting AI think ahead, basically, preparing during its downtime to be faster and cheaper when you actually need it.
Especially for those stateful applications we keep mentioning.
Yeah, it's just, well, another fascinating angle in this whole AI explosion that's happening. We are definitely just scratching the surface.
So much research, so many directions. It's hard to keep up sometimes.
Tell me about it.
Yeah.
But it's exciting stuff. Anyway, thanks everyone for tuning in and spending your time with us on this deep dive. If you enjoyed it, please do subscribe if you haven't already. It really helps the channel out.
Yeah, thanks for listening.